not see it. I'm going to talk about some work that Shumangshu, Amit Givon, and I did this summer, and some related things that came earlier, which I will explain as background. Just in a way of kind of an introduction, the main thing that motivates this specific part of the work, so this is a kind of part of a bigger project. This part of the project is motivated by the question of what happens when we deal with singularities such as Big Bang and Big Crunch singularities, black hole singularities in string theory. And of course, we've been all working on holography for many years now. And a natural question is whether holography is good enough to deal with this. There was a lot of talk about this in the context of ADS from actually even before probably this paper to the very recent paper that I mentioned here. But I think it's fair to say that the understanding of this issue is kind of rudimentary at the moment. And what I'd like to do here is to talk about these issues in the context of some other holographic models that have to do with TTbar deformed CFT and some related theories in the context of holography. I should warn you that the results that I'm going to present are pretty preliminary. They definitely need much more development, but as I will try to indicate, there are many reasons for studying these theories that I'm going to talk about. So it's definitely worth pursuing this subject further. As I'll say later, this whole story is a convergence of various lines of investigation. And so I could start the story in a few different places. I chose to do it this way because it's very convenient for where we're going, but I could have done it some other way. So let me start by reminding you of some old stories. So it's already around 30 years since Cullen, Harvey, and Strominger showed that if you take K Navier-Schwarz 5 branes in type 2 string theory with a world volume R5 and look at the geometry near them, it looks like this. There's a factor of the world volume of the branes and the transverse space, which is here described in spherical coordinates. So phi is the radial coordinate and S3 are the transverse spheres. When you go to the near horizon geometry, the radial coordinate is described by a linear dilaton worldsheet CFT, sort of textbook subject in string theory, with the slope of the linear dilaton being proportional to 1 over the square root of the number of 5 branes. And the sign of it is such that when you go away from the 5 branes, the string coupling goes to 0. And when you go towards the 5 branes, the coupling grows and eventually blows up. The 3-sphere is described by the so-called SU2-WZW superconformal model, with the total level being the number of 5 branes. Now, string theory in this geometry was, after the advent of ADS-CFT, proposed in this paper to describe holographically the so-called little string theory. It's a certain non-local theory with the Hagedorn density of states. And there's been a lot of work on little string theory, and in particular, this approach to it over the years, but a lot remains to be understood. In fact, one of the main motivations for my involvement in this work is precisely to better understand this theory. Now, in his famous 97 paper on the ADS-CFT correspondence, Maldacena proposed replacing the R5 that the 5 branes are wrapping by a compact space, let's say S1 times T4, or maybe K3 here is also fine. And adding to this system a large number of strings that I will call P that wrap the S1 and are located deep down the throat of the 5 branes. Now, the 5 branes, as I mentioned a moment ago, lead to a growing string coupling in their vicinity. The strings have the opposite effect. So when you put both, the string coupling stabilizes at some value that goes like this. Of course, if P is very large, the number of strings, then the coupling is small, and we can study the theory using perturbative string techniques. The geometry in that region where the string coupling stabilizes is ADS3 cross S3 cross T4. The ADS3 factor is what came from the radial direction away from the 5 branes, the S1 that the strings and 5 branes wrap in time. And the rest is the same as before. This ADS3, importantly for us, is described by some SL2R WZW model at a level which is equal to the number of 5 branes. Now, of course, the main reason Maldacena was even doing all of this is to investigate the ADS-CFT correspondence. In other words, this background is supposed to be holographically related to a 2-dimensional CFT. And the question is, what is that CFT? This question is still open today, more than 20 years later, although we have learned a lot about it over the years. And I'm not going to obviously review what we've learned, but I'll mention the one thing that will be important for me about what we've learned, which is the following. So these people listed here showed that in ADS3, as opposed to higher ADS spaces, the spectrum of the theory that I just described has a continuum above a gap. And the interpretation of that continuum is that strings that wrap the S1 have a finite barrier for escaping to infinity. This is a kind of qualitative semi-classical way of looking at it, but you can make the statement mathematically precise. After all, you know, the WZW models are exactly solvable, and this is such a model. And so what Maldacena and Uguri showed is that if you look at the spectrum of these strings that can escape to infinity and carry some continuous momentum in the radial direction, the spectrum of those things, if you look at strings winding W times around the circle, is given by a formula like this that I'm not going to review the details of, where we have the usual oscillation levels of the left and right movers on the strings, and the radial momentum of the string is proportional to this thing I call S here. So that formula describes exactly the spectrum of these long strings with arbitrary radial momentum. And what is interesting about it is that if you do some standard manipulations, which again, I don't think there's a need for us to go over, I'm happy to do it, but this is not really the purpose of this talk. The point is that if you look at the spectrum of strings winding W times around the circle, that spectrum can be written in terms of these dimensions that I call HW as related in a simple way to the spectrum of states with winding 1. And what's interesting about this formula is that that's exactly what you would get if you took a CFT which consists of all the states with winding 1 here. If you set W to 1 here and you look at all the states with those quantum numbers that I described, and then form this combination, that's the same spectrum as what you would get in a symmetric product of this CFT-M.
David, is the first term in that formula sort of the oscillator energy, and the second term the Casimir energy?
You're talking about this formula, yes?
No, the one below.
Here?
Yes.
Yeah, that's the dimension of the twist field, the kind of ZW twist field, as you know, when you take, for example, this thing plays an important role in discussions of Renyi entropy, right? So if you look at M to the W mod ZW,
So can I think of it as the difference between the Casimir energy of one long string of length W and the Casimir energy of W strings of length 1?
I think so, yeah.
Okay, and the first term is oscillators. So it's exactly the same mechanism as the one that works for the symmetric product.
Yeah, I mean, that's right. So I'm about to say another thing about it. But the basic point I wanted to make in this transparency is that around the year 2000, this led a bunch of people to conjecture that the theory that describes just these states, the long strings, technically that belong to the continuous representation with a certain spectral flow that gives rise to W, is just a symmetric product like that, something of the form M to the P modus P, where M consists of all the long strings with W equal to 1. Now, that statement then was made kind of more precise in that Zyberg and Witten paper that I mentioned, I think, here, who pointed out that the theory with W equal 1 in this case is a sigma model on a space like this. So basically, if you just replace the ADS3 by the linear dilaton space corresponding to the radial direction, that's the sigma model M in that case. However, it's not exactly the same linear dilaton that I started this talk with, namely the slope of this linear dilaton is different, and even the sign of it is different. So as you look at these strings moving away out of the throat, the string coupling on them actually increases. And that's an interesting, so the physics of long string is strongly coupled when they try to leave the condensate. And that is an important separate story that, again, one could give a whole seminar about, but this is not what this seminar is about. Now, I think what Shiraz was just talking about is related to here. So in the days of so-called matrix theory in the mid-90s, people pointed out that if you have a string winding a circle and the theory of small excitations on that string is given by some sigma model M, then the symmetric product M to the n modus n provides a description of the Hilbert space of free strings with total winding n. So if you look at the untwisted sector states of this orbifold, these describe strings winding once around the circle. ZW twisted states describe strings with winding W. So if you have W strings that connected and made one long string with W equals to some higher integer. And in general, there's some more complicated story to do with conjugacy classes of the symmetric product. So this is all kind of fine. Now, here I'm just pointing out the things that are going to be important for me. And one of those things is that, you know, when I say that the symmetric product describes the spectrum of the long strings, I really only mean the spectrum of long strings. Correlation functions certainly are not described by this. It's very similar to what happens in Liouville theory, for those that are familiar with it. You know, if you have a scalar field with an exponential potential. If all you're interested in is the dimensions of operators, you can go to the region very far from where the exponential potential is essentially 0 and study the spectrum there. But if you want to calculate correlation functions in Liouville theory, you certainly cannot do that while staying away from the potential, at least not for generic correlation functions. And so the same thing happens here. Another useful comment is that the symmetric product does not seem to describe well the full theory. There are some arguments that the full theory can be described by a symmetric product with a kind of larger M, but it's certainly far from being established. Now, there are many generalizations of this. I'm not going to discuss them here, but it's useful to know that they exist, where you look at, instead of just 5 branes filling, say, T4 cross S1, you look at curved five branes wrapping various surfaces, or equivalently dynamics of strings propagating near singularities of various Calabi-Yau manifolds. And near such singularities, one typically has a very similar story. There is a linear dilaton space time that you get, and if you want to get an ADS3 background, you just throw a large number of strings into this linear dilaton throat, and you get some ADS3 background. The reason it's useful to think about these generalizations is that every time somebody tells you some story, you can ask, is this story valid in this whole class? Because this is a large class of examples, and as opposed to just is it specific to some particular example? And so, for example, the symmetric product structure of long string that I just described is valid for all of those things. So any questions about anything that I said so far? Okay, so now the main hero of today's story.
Sorry to interrupt, please excuse me, this is Sandeep. I'm a little confused, not having worked in this, about the space-time, that is the boundary CFT and the world sheet CFT, sorry. So these various descriptions, for example, the symmetric product with the dilaton, they are all on the world sheet, right? As the signal?
No, so
sorry about this, I'm getting a bit confused. Yeah, go ahead.
There's no need to apologize, and that's why we're here.
Okay,
so you can consider a string theory in a background like this, for example, ADS3 cross S3 cross T4. Now, of course, you can describe it on the world sheet by taking the S3 to be some SU2WZW, the ADS3 some SL2R, and T4 that you're familiar with from the, the Rhine. Now, the question is, what is the space-time physics? And the space-time physics is described by some CFT. Now, we don't know what the CFT is in general, but there is indeed some kind of deep interplay between worldsheet and space-time. So there is indeed, it's a confusing point. This here, I can view in two ways. One as the bulk geometry that, like the analog of, say, ADS5 crosses 5, or as some sigma model on the worldsheet of the string. Here, when I said that Zyberg and Witten showed this, this is not a world. So the base space on which this lives is the, if you want, the base space of the boundary CFT. Okay.
Okay.
So the claim is, so basically what Zyberg and Witten showed is that essentially is that if you look at the boundary CFT that Maldacena was after in 1997 contains a sector which looks like this sigma model to the power P mod SP in the sense that I just described. So yeah, so it's very important that here, viewed as a two-dimensional theory, the base space of this is the worldsheet of the string, whereas here it's the actual boundary coordinate.
Okay, thank
you.
So they're definitely not the same. That's an important point.
Sorry, David, when you say viewed as it's a sector, given that it's interacting with something else, the sense in which precise sense in which it's a sector relies on the fact that there's an asymptotic region where it decouples from everything else. Is this right?
That is correct, yeah. Now, you can ask, how is this business that there is a decoupled region consistent with the fact that the coupling increases as the string moves towards the boundary? And the answer is that indeed, this is a subtle issue. And what I'm really saying is that there is a long region in the target space of the boundary theory in which the string coupling is small, and we can trust this description as far as the dimensions or energies of states in the theory. It's a little bit, like, we don't really have an example like this that we've ever worked out in conformal field theory. But if you want to think about something that has some of these features, so I don't know if you've ever looked at the cigar conformal theory, just viewed as a conformal theory. You don't have to worry about embedding it in anything. So that theory has the property that it has an infinite cylinder region where, as you say, kind of everything is free. Some states live in that region, like there's a continuum of states that live in that region, right? Momentum along the cylinder could be anything. And then in addition, there are some states that live near the tip of the cigar. So there are some delta function normalizable states, and there are some normalizable states near the tip of the cigar. And so the analog of what I'm talking about here in that case is that there is a sector of the theory which corresponds to the delta function normalizable states, whose dimensions you can read off without ever talking about the region near the tip of the cigar. You can just look at the cylinder. However, if you wanted to calculate any correlation functions, that's where the good news would stop. You have to solve the whole theory.
Sorry, and one more quick question, please.
Yeah.
Could you give even some very rough intuition for why the coupling increases towards the boundary for this thing?
Yeah, that's an interesting question. Well, one way to think about it is the following. So you know that the full theory, this theory, like viewed as a bulk theory, if you asked what is the actual high energy spectrum of this theory, the answer is it's dominated by black holes, by BTZ black holes, right? And so if you go to very high energies, it must be that those strings that are trying to leave the condensate would form bound states that are these black holes. And so if the coupling was not increasing when you go that way, there would be some kind of contradiction because then you would say that this Zyberg-Witten description would be valid the whole way up to infinite phi. And that is in contradiction with the fact that we know that states that are energetic enough form black holes. I think there are some other ways of saying this, but again, this is not really any other questions. Yeah, so there is an interesting story that one can tell that generalizes what I just said. So suppose we took the near horizon limit of the 5 branes, as we do here all along, namely we're looking at the LST limit, but we did not choose to take the near horizon limit of the strings. We looked at the whole geometry from very far from the strings to very close to the strings. That geometry is also known. I wrote it here. So you see what happens here is that when phi, the radial coordinate, goes to infinity, this F1 is nothing, and you can easily convince yourself that this is just the geometry that Cullen, Harvey, and Strominger wrote all those years ago without the S3 and the T for 5 branes. But when you go to phi goes to minus infinity, this term dominates, and you can convince yourself that this is just ADS3 times, of course, this factor that goes along for the ride. So this is some kind of interpolating geometry, and it interpolates between these two things. If you wish, I'm just to go from the near horizon limit for the strings to the full thing, I'm just adding the 1 in the harmonic function of the strings. Now, you can ask, what is this? Well, from the point of view of the UV theory, from the point of view of these little strings, it's just some description of a state, a normalizable state that contains p strings wrapping that circle that I was talking about before. But from the point of view of the infrared theory, the theory that lives at large negative phi, this is an irrelevant deformation of the 2-dimensional CFT that is dual to the ADS3. How do I know that it's irrelevant? It's because it changes the form of the boundary, right? Without the 1 in the harmonic function, as phi goes to well, you know, without the one in the harmonic function, all we have here is just ADS3. And with the one in the harmonic function, the structure as phi goes to infinity is different. So by definition, something that does that is an irrelevant deformation on the boundary. And so a question that you can ask is, what is that irrelevant deformation? Now, normally we would say there's no way we're going to be able to answer this question. It's basically just a bulk analog of the question, how do you flow up the renormalization group in field theory? And you know the answer is that you don't. It's an ambiguous procedure. However, as pointed out in these papers, here the situation seems to be much better. And the reason it's much better is that it's basically the deformation on the worldsheet of the string that does that implements this addition of the one to the harmonic function, is something simple. It is a tearing type deformation. So I'm not going to talk about all the details of that statement. Again, this is not like this separate seminar that some of you heard me give that has to do with that. But basically, the kind of lightning version is, I told you that the ADS3 factor in the string theory is described by some SL2R WZW model. It has these currents, J plus, J minus, and J3. From the point of view of the spacetime theory, these currents give the SL2R subgroup of Virasoro, which the theory must have. It's a conformal field theory on the boundary. So J3 gives L0, J minus gives L minus 1, and J plus gives L1. And it turns out that the background that we're describing, this thing with the perturbation of the harmonic function, is just a very simple tearing type deformation of the worldsheet sigma model. So, you know, as Sandeep reminded us before, there's some kind of balancing act going on here. You can think on the worldsheet, you can think in the bulk description, and you can think on the boundary theory. So on the worldsheet of the string, you have this deformation that corresponds in the bulk theory to adding the one to the harmonic function. And the only thing that I still need to address is, what does it mean in the boundary theory? But before I even do that, I want to point out that it's a very odd situation that we find ourselves in, that on the one hand, Wilson tells us that we should not be able to study irrelevant deformations of a CFT. But on the other hand, in this particular case, it's on the worldsheet of the string, it's holographically related to something that's exactly solvable. So what is going on here? And the answer is interesting. The answer is that you can show that the addition on the worldsheet of the string of this J minus bar term that I was talking about here corresponds in the dual theory in the boundary CFT that is dual to this ADS3 to adding a certain operator to the Lagrangian of the boundary theory. Again, it's a long story that I'm not going to tell you, but this operator has the following interesting properties. First of all, it has scaling dimension 2,2. That is consistent with the fact that it's irrelevant, that it changes in the bulk description the form of the boundary. It is quasi-primary. The leading term in its OPE with the stress tensor goes like 1 over x minus y to the 4. All of this you can prove in worldsheet string theory. And one way to think about it is, if you forget for a moment about all this string theory stuff, if you want some simple way of thinking about this operator D, if you took some CFT, which is a symmetric product, in other words, where the stress tensor is a sum over the copies of the symmetric stress tensors of the various components, then this D behaves like this kind of operator. So for example, you see you can just do the exercise in your head. If you look at the OPE of T with D, there's a 1 over Z to the 1 over X minus Y to the far term in this OP, and its residue is just T bar. So that's something that would happen if you just did the symmetric product. And I'm saying independently, this precise thing happens for this operator D in string theory on ADS3. Now, it's kind of odd that I'm talking about symmetric product after spending some time telling you that string theory on ADS3 is not dual to a symmetric product, likely. But the reason that this kind of toy example is still useful is the following. I also said that long strings with arbitrary radial momentum are described by a symmetric product. This is this thing I said that's known already for 20 years. And so it's a legitimate question, how does this operator D look in the theory of the long strings? Now, what I mean precisely by that is that adding this D operator to the Lagrangian of the boundary theory must give some, well, must change the spectrum of these long string states. And that change must correspond to adding to the Lagrangian of the symmetric product theory that describes those long string states something. So what is that something? Okay, so basically, despite the fact that we do not know what is the boundary theory, the full boundary theory, the fact that we know what the boundary theory is for long strings allows us to ask this kind of question. And the answer is what I write here, that it's indeed precisely this operator. It's a sum over copies of these TTbar operators in each block of the symmetric product. Remember, the symmetric product block is just this Seiberg-Witten theory on a single long string. Now,
so this means that the full theory remains a symmetric product.
So the theory of the long strings
yes.
Still remains a symmetric product. However, the building block of the symmetric product is no longer conformal. It is the Seiberg-Witten theory deformed by TTbar.
Right. Thanks.
Okay, now this logic leads to an interesting conclusion, just coming from this approach, that what you learn from string theory is that the TTbar deformation of a CFT must be solvable, despite the fact that it is irrelevant. You learn it from kind of string theory. Now, it's kind of a curious situation because everything I said so far was known, as I indicated, more than 15 years ago, but it took until 2016 and the work of those two groups, let me call them the Russian group and the Italian group, to realize that this is indeed the case, you know, that the TTbar deformation of a CFT is indeed solvable. And the way it happened is basically that two lines of investigation converged at that time. What I was talking about now, and some completely orthogonal approach that was pioneered by Zamolodchikov in 2004, based on integrable field theory. There was actually a third line of investigation that led to the same conclusion by Dubovsky and company, which was motivated by QCD strings, but I don't have time to talk about it now. This is some disclaimer that I guess I'm a little bit behind on time, so let me not worry about it too much. I mean, this convergence, this overlap of ideas between these three lines of investigation is not really complete. As I said before, this D is not really the same as TTbar. We don't understand exactly what it is because we don't know exactly what ADS3 corresponds to. The relation between QCD strings and TTbar deformed CFT is also not completely well understood. But there is a kind of a feeling of a general convergence of ideas that seems promising here. After all of this was realized, the string theory picture was used for all sorts of studies of all of this, the TTbar deformed CFT, all sorts of generalizations of TTbar deformed CFT. And it was actually found to be very useful. Like in some cases, the approach that I outlined here was used to reproduce known results from field theory. In some other cases, especially in all these generalizations, there were a lot of new results that were obtained from string theory. In some cases, they were reproduced later from field theory. In some cases, not yet. And in addition to all of this, this also gave a lot more confidence to our this idea that I mentioned before, that the long string sector of ADS-ray is described by a symmetric product. So as I said, this is a nice story. I don't have time to talk about it. I want to go in a different direction.
Quick question, please. So does the coupling constant turn around now in this new deformed theory? Does it start going down as you go towards outside instead of?
Are you talking now in the bulk?
The coupling constant of the long string CFT.
Oh, yeah. So, well, no. Well, I mean, I'm not sure how to think about that.
Isn't there a clear value of the dilettante?
I wouldn't say, no, I wouldn't say that it turns around. Why would you think it turns around?
I was somehow expecting it to become the strings in the NS5 brain background.
No, yeah, so I understand your picture, but yeah, so no, so as you probably remember, there is this story with, which I think you wrote papers about, with the throat of the Higgs branch versus the throat of the Coulomb branch of the 5 brains that was popular in like 97 or so. And the point is that these two throats are separated by an infinite amount. So even though you turned on this this TTbar deformation, like this deformation that adds the 1 to the harmonic function, you're still dealing with the Higgs branch throat, and you're not getting out of the throat of the 5 brains. I think the picture you expect is the one that would be possible if the strings could leave the throat of the 5 brains and go into the Coulomb branch. But that is not something that is happening here. That would be like saying that you cannot anymore use the little string theory of the 5 brains as the UV theory. But you can, as you'll see in a second.
Okay, thank you.
Yeah, so yeah, so where was I? So the way to go to the next step in our discussion for today is one way is this. These two groups, this Russian group and Italian group, wrote a formula for the energies of the deformed states in terms of the energies of the undeformed states. And what they found is that if the coupling of this TTbar has one sign that I will call positive, the energies are real, and in fact, this formula interpolates between a Cardy spectrum at low energies and a Hagedorn spectrum for sufficiently high energies. So that's an interesting thing in its own right. There's some non-locality in this theory that has been explored a lot in recent years. But the other thing their formula does is that if you take the coupling to be negative, if the energy, say if you set the momentum to 0, if there's a minus sign in front here, beyond a certain energy, you get complex numbers, which is impossible because if it's a unitary theory. So there's basically an upper bound on the allowed energies of states. Now, the attitude that these people, these two groups took to this fact is basically to restrict to positive coupling. The Russians said that there's no vacuum for negative coupling. The Italians kind of worked with positive coupling, never even mentioning the negative one. But then a funny thing happened that I'm sure surprised those people to some extent. And that is that in the first paper on holography that was written by these people, it was argued that for negative T, there is a dual, which is string theory on ADS3 with a UV cutoff at some finite radial position. And moreover, since that time, probably like 70% of the papers on this subject talked about that theory, holography with negative T. I say it's kind of funny because that's not the theory that these people were focused on. They were focused on the theory with positive coupling and would probably say that the other one doesn't even exist. Now, in our approach to this whole business, the case of positive coupling is also much better behaved than that of negative coupling for a very simple reason. For positive coupling, we have this kind of geometry. I'm only focusing here on the three-dimensional geometry that deforms the ADS3. And so it interpolates, like I said, between ADS3 and some linear dilaton space. But for negative coupling, this F1 has a -1 in front of the constant term rather than a +1. And then all sorts of bad things happen. As you see, for very small r, it doesn't matter if it's a -1 or a +1, you get your ADS3. But if this is a -1, then at some finite value of r equal to r1, you get a singularity of the geometry of the dilaton. If you continue past the singularity, F1 flips sign, and then suddenly T behaves like space, X behaves like time. It all looks kind of bad. And our initial attitude to this was to say, yeah, that probably doesn't make sense. And so we didn't really worry about it too much. But this spring, we decided to take another look at it. And that was for two reasons. One is that if all our colleagues are right, that the theory with negative T makes sense, by which I mean the TTbar deformed CFT with negative coupling, it is very unlikely that our version of it doesn't make sense. And I would say vice versa. If our thing with negative T doesn't make sense, it's highly unlikely that TTbar deformed CFT with negative coupling makes sense. And the other reason is that it's a kind of amusing fact that the theory with negative coupling formally preserves the same amount of supersymmetry as the one with positive coupling. So say for the case of these flat 5 branes and strings that I started the seminar with, it is 4,4 supersymmetry. It's kind of strange to say that a theory with this much supersymmetry is sick. And if it is, we would like to know why it is sick. So what we decided to do is think of what calculations we can do in the theory with negative coupling and see if we get nonsense out of those calculations. So we immediately thought of two things that we can do. One is thermodynamics. So as you know from ADS-CFT, to study the high energy thermodynamics, you basically need to construct black holes in the relevant bulk background. So we constructed the black holes in the backgrounds that we're dealing with and looked at the thermodynamics. I will show you what we got. Of course, there are more details in the papers, and you can judge for yourself whether you think this is the thermodynamics of a sick theory or not. The second calculation is we looked at probe strings that wind around that famous circle and move in the radial direction of that singular space-time. As I mentioned before, there should be an upper bound on the energies of the states of the deformed theory, and those states are precisely such strings. So what we wanted to see is what is the origin of this bound on the energies of states that you learn from the TTbar formula, from this formula with negative lambda in some kind of semi-classical quantization of the bulk theory. And since it's already getting late, let me already tell you the bottom line of this. These two calculations, we don't see anything particularly sick about the theory with negative coupling. If the theory is nevertheless sick, it's for some reasons other than the ones that are revealed by the calculations that we did. Yeah, so as I anticipated, I don't have that much time, but fortunately all the details are in the papers. So all I want to do in the remaining, let's say, 13, 14 minutes, is just to give you some qualitative picture of what's in those.
David, maybe I can say that we're not at all strict about time. So,
Okay.
don't need to feel.
Yeah, but I know how I feel if somebody talks for an hour and a half and it's not great. So, well, yeah, so let me tell you about the two calculations. Let's start with the thermodynamics. So we have to construct a black hole in this deformed geometry with the one in the harmonic function of the strings. And let's first check that everything is working fine for positive coupling, where we kind of feel like we know exactly what should happen. And so here is the situation. So we have here all these harmonic functions that you're familiar with from other contexts, maybe even from this one. So we have this F1, which is 1 plus R1 squared over R squared, the harmonic function of the string. We have F5, which is the harmonic function of the fibranes. We got rid of the 1 in that harmonic function in going to the little string theory limit, the near horizon geometry of the fibrane. That's what this wiggle means. And we have the usual expression for the black hole thing. So R0 is the location of the horizon. Now, R1 started its life, where is it? As just the strength of the source. It's proportional to P, the number of strings, and to G squared, which is the usual story that, a single string gives an effect of order G squared in the geometry. It's down by a factor of G squares from like just changing the geometry. However, when you turn on, when you add energy to the system, when you make the system non-extremal, both are zero. So you're familiar with the fact that the position of the horizon is a good measure of the energy, but R1 also changes when we do this. So when you do the calculation, you find these two expressions. The position of the horizon depends on the energy in this way. Epsilon C is going to be important for us, but for now, it's just some constant. So, like when epsilon goes to 0, R0, the size of the black hole goes to 0, obviously. But R1 also depends on the energy in this way. That's what you find from solving the gravity equations of motion with this source.
R1 was the location of the singularity where the space is?
Yeah. So there's that's something I should stress. So we had two formulae. One is when we, in the language of TTbar, we turn on the deformation with positive coupling. In that case, there is no singularity. The sign here, both signs are plus. That is the case I'm dealing with now, okay? And then there was a second calculation, which was for negative sign of the coupling, where we have a -1. In that case, R1 is the position of the singularity, but right now I'm doing this case where there is no singularity.
Thank you.
And the reason I'm doing that is just to make sure that I'm not making stupid algebraic mistakes, because as I'll mention in a moment, I know exactly what I'm supposed to get. So it's just some kind of warm-up exercise. Yeah, so R1, well, you'll see in a second what R1 is, like what is the physical interpretation of R1. So you see, what happens is if you take the ratio between those two formulae, you find that the ratio between R1 and R0 is this thing. Actually, even at this level, it's easy to see what R1 means. So, R1 is the value of R at which this geometry makes the transition from ADS3, right? If R is much smaller than R1, this is ADS3. If R is much larger than R1, this is a linear dilaton space. So in the bulk, this is the meaning of R1 for positive coupling. It is the value of R at which we make this transition. Now, if you take the ratio of these two formulae, you find that in terms of the energetics, this is what it is. the ratio of R1 to R0. And if you do black hole thermodynamics, you find this kind of expression for the entropy. Now, so what happens here is the following. When the energy is small enough, this epsilon is the energy in units of the size of the circle. When the energy is small enough, then this term dominates and we just get Cardi entropy. When the energy is large, you get, this is much larger than this, and you get Hagedorn. So there's clearly some interpolating function here that interpolates between Cardi and Hagedorn. And the Hagedorn in question is with this inverse Hagedorn temperature. Here it's clear what's the physics, right? So as the energy increases, you're dominated either by this or by this. And if you plug in the numbers, you will see that the transition between those two regimes happens precisely at the scale epsilon c, which I wrote here. So there are two kind of completely equivalent calculations. One is which term in the square root dominates, are you Cardi or Hagedorn, and whether R1 is larger or smaller than R0. And the physics, again, is completely clear. If R0 is very small, then the horizon of the black hole is at very small r. In other words, it's in the regime in which the harmonic function of the strings is just dominated by the R1 squared over R squared term. In other words, you're deep inside ADS3. So when R0 is much smaller than R1, the black hole is in the ADS3 region, the horizon is. And when R0 is much larger than R1, the horizon of the black hole is deep inside the linear dilaton regime of this geometry. And correspondingly, you can check just by looking at this that when epsilon is much smaller than epsilon c, this entropy has Cardi behavior. And when epsilon is much larger than epsilon c, it has Hagedorn behavior. So it's everything fits like a glove in terms of the geometry of where the black hole is in the bulk geometry and the thermodynamics.
And the coefficient of the Hagedorn is the same as the one that you got from the point of view of the sigma model of the long strings?
No, you mean
Hagedorn temperature.
Yeah, you can say it's a confusing way of saying that, but well, let's call the answer yes and no. I mean, so what you're referring to is where was this formula? You're referring to this here. Yeah, actually, so first of all, here there is no Hagedorn, right? This is just some sigma model corresponding to these long strings.
But after the deformation, there was a Hagedorn, you told us, right?
Sorry. Yeah. No. So yeah, so that is not the Hagedorn that you would get from this. This is some business with C versus C effective. So this theory has a central charge 6K, but it has a much smaller number of states, which has to do with its effective central charge, which is of the order.
Sorry to interrupt, but after the deformation, you said that the space-time long string theory had a Hagedorn growth, and there's a coefficient in that Hagedorn. And does that agree with the black hole?
Okay, so let's take a look. Okay, so what I said, so this, you're talking about this here, right? Yeah, so the answer to your question is no, it's not that Hagedorn.
Okay.
But it is a Hagedorn. So remember that what I said is that the block of the symmetric product has central charge 6K.
Yes.
Now, if you had a unitary theory with central charge 6K, and you did this to it, you would get a certain Hagedorn, and that is this Hagedorn. This Hagedorn. Now, if you have, if the block of the symmetric product is a theory which has many fewer states, then you get some other Hagedorn in it, and that's a smaller Hagedorn.
Okay.
Now, this Hagedorn that you get here is the Hagedorn of the bigger theory, and it's related, technically it's related to the fact that the full string theory on ADS3 cross S3 cross T4 is a conformal field theory which contains the SL2R invariant vacuum, you know, so the boundary theory does, whereas the Seiberg-Witten block theory does not contain the SL2R invariant vacuum. Now, it's all like, again, there's a huge part of the story that is missing here, and there's a good reason why it's missing. It's that I'm focusing on these other things. But yeah, bottom line is that it's not that Hagedorn.
Thank you.
Sorry, David, can I just ask you again a naive question, excuse me, which is, so it seems that this Hagedorn temperature then just characterizes the little string theory. That is, P disappears, the effect of the strings by
that's right. And that makes perfect sense, right?
Yeah.
Because that Hagedorn appears when the black hole, when R0 is such that you don't see the strings, right? Where F1 is 1. So this Hagedorn is a feature of just the fibrines, as you absolutely correctly point out. And by the way, you know how I said in the beginning here that one of the main reasons I'm interested in all of this is to understand the theory of the fibrines? Well, if you think about it for a moment, your observation is precisely the reason why you can hope to push your way up from the theory of the strings and the fibrines that we can hopefully understand, because it's just understanding how ADS-CFT works. And then use these techniques to push yourself up the RG to the place where you're just studying the fibrines. So you're absolutely correct that the P disappears.
Thank you.
And you can see exactly how it disappears, right? The fact that P disappears is related to the fact that the energy, crossover energy, goes like P. Yeah, but these are all very good questions.
Sorry, one more quick. Sorry, David. Once the block of the long strings, you said had a different Hagedorn. But now when you symmetric product, any conformal field theory, you get some effect, some new Hagedorn kind of scale. And I was wondering whether the Hagedorn of that symmetric product of this block agreed with your spacetime Hagedorn.
Well, so my understanding is that, so first of all, again, when you say Hagedorn, so if you have a CFT and you take the symmetric product, it's still a CFT, right? So the growth of the entropy is always like the energy.
Right. But there's a regime between energies of order 1 and energies of order n where it looks exponential.
Yes. So in my language, so you're saying you can look at all sorts of intermediate regimes.
Yes.
Okay. So in this language, you say, let's not go all the way to where I can neglect this relative to this, but let's look at some intermediate regime.
Right.
Energies that are much larger than kind of 1, but much smaller than this epsilon c.
Right.
Yeah, I haven't thought about it carefully, and I don't really have any. So the only thing I can tell you for sure is that this black hole interpolates smoothly between all these regimes, and so in principle you can look at that.
Thank you. Yeah.
But I haven't really looked. I just looked at energy is much larger than epsilon c, and energy is much smaller than epsilon c. Yeah. So anyway, this was all a warm-up exercise. And the bottom line from the warm-up exercise is that we have this interpolation between small black holes whose horizon is deep in the IDS3 regime, and the entropy exhibits Cardy growth, and large black holes whose horizon is in the linear dilaton regime and that exhibit Hagedorn growth. By the way, it's also true that the specific heat of these black holes is always positive. Of course, their energies are not bounded from above. The temperature is bounded from above by the Hagedorn temperature, and you'll see in a moment why I even bother to mention this fact. Now, let's look at what we're actually interested in, which is the negative case. Yeah, I'm kind of feeling bad. I mean, I know Shiraz said I can talk until midnight, but let me try to finish like within, say, 10 minutes. So let's look at what happens.
We don't let the speaker go till at least 1.5 hours, David. So, sorry.
Really? Okay. Well, I don't think you went to, I think Amit will and Shumangshu will tell you that the last thing you want is to let me speak.
No, sure.
Well, anyway, so let's look at the case we're actually interested in, the case with the singularity. So now F1, I copied it here. There is the black, so we have a singularity at R equals R1, the horizon at R0, and the same F5 as before. Now, but it's still an interesting situation because just like in the case of positive coupling, R1, when we started out, was just some number, but when you start adding non-extremality to the system, making a black hole, the R1 changes together with R0. So of course, R0 changes because you're turning up the energy. I mean, for example, you see that when epsilon, the energy goes to epsilon C, remember our famous epsilon C that we were talking about before, R0 even blows up. So like you would think that things will go horribly wrong for us here because we had this singularity, right, at R equals R1. The black hole keeps growing without bound until the energy reaches this critical energy that I mentioned in the TTbar context before. So you would think that at some point you will hit the singularity, but no, you don't hit it because R1 also changes with the energy and it also blows up when the energy goes to the critical energy.
So, David, your analysis here now is in supergravity, unlike the zero temperature analysis, which was conformal field theory exact, right?
That is accurate, yes. Right now, technically what I'm doing is taking K to be very large and P to be very large and doing an analysis in supergravity. But that's kind of good enough for our purposes here of studying singularities and stuff. Like at R0 equals 0, we have this way of studying problems with K of order 1, but P large because we want the string coupling to be small. And here I'm doing supergravity, absolutely right. Anyway, the ratio between those two things, you can compute just like before. Remember, that's what it was in the case of positive coupling. And there it could be less than 1, larger than 1. I made a big deal out of all this. But now it's always larger than 1. So we have a picture like this. If the dashed red line is where the singularity is, and the yellow blob is the black hole, as we increase the size of the black hole, it pushes the singularity out. And even when R0 becomes giant, when the energy approaches the critical energy, it's still this kind of picture. So we can do black hole thermodynamics because we are not on top of, it's not like there's a singularity inside the black hole or something.
Sorry, is the curvature in string units bounded at R0 as R0 becomes?
Yeah, I mean, unless of course you go to, you take this limit. So if you go to epsilon equal to epsilon C, then all of this stuff blows up in your face. But if epsilon over epsilon C is some fixed number strictly smaller than 1, which is what all of this is sensitive to.
Thank you.
You're good. Yeah, so this is what you get. Okay, so first of all, this means that you can do black hole thermodynamics. The inverse temperature you get is this. So what is happening here is this. The temperature goes to 0 when the energy goes to 0. It diverges, as you can see from here, when epsilon approaches the critical value. And the entropy is some finite thing. The specific heat, you can easily convince yourself that this corresponds to is always positive. And this curvature business that Shiraz just mentioned is just this statement that when epsilon goes to epsilon c, the temperature goes to infinity. And then, of course, it doesn't look great. So here is the summary of this calculation. We get thermodynamics that make sense for both signs of the coupling. For positive coupling, as we said, the energy is not bounded from above while the temperature is. That's the Hagedorn story. For negative coupling, the energy is bounded from above, but the temperature is not. The specific heat is always positive. And for negative coupling, the entropy is also bounded from above. Like if epsilon has to be smaller than this epsilon c, this famous value that, where was it? This value here. And you can just plug in epsilon c into the formula here, and you'll find some finite value of the entropy. And that, of course, is if this theory continues to make sense as one probes it in various ways, is an interesting situation, right? You have a theory with a finite entropy that makes sense, a quantum theory with a finite entropy. So that's what we get from this exercise. So any last thoughts about?
Is the conclusion that the energy is bounded and, from above completely robust? Since you're getting that,
I would say yes. I would say yes. That so you see exactly what I did here, right? That I constructed. I should say that there is some paper by Apollo and collaborators, paper from China from about a year ago, that I think construct a similar black hole in some other coordinates, where it kind of formally looks like you can go above that energy, but this is some kind of analytic continuation that you really don't want to do. If you do it, it looks terrible.
I was thinking, and this is probably weird, but I was thinking that as epsilon approaches epsilon c, you're getting a supergravity solution you can't trust. So could it be that the actual string solution allows you to go further to infinite energy?
I would say I cannot exclude this, but
it doesn't sound likely. I agree.
I don't have any reason to think that way. Yeah, so let me.
Sorry, David, sorry to slow you down, but just to make sure I understand the picture. So as you explained, the idea for the positive coupling, when there was a +1 in the harmonic function, is that maybe starting from this, 2D CFT, turning on this TTbar coupling, we might hope to describe little string theory, as you were saying.
Right.
And that's really beautiful. And now turning the coupling to negative, I suppose the continuation of that would then be that you are able to, the hope is you can describe these spacetimes with this sort of singularity that you're seeing.
Using the same kind of TTbar story.
Right, I guess.
I mean, again, like as I stressed in the beginning, when I started talking about all this stuff, in field theory, it's an open problem whether this story that I'm pointing to exists for negative t or lambda.
Okay.
But if you allow string theorists to vote, like string theorists voted that the negative coupling makes sense. So now it's on the field theorists to explain how it makes sense.
Okay.
And so I'm assuming already that something like this was done, okay?
Okay.
And moreover, like our version of it was also analyzed this way.
Okay.
All these things are examples of what I meant in the beginning when I said that the results are preliminary and that there is a lot of work.
That's fine.
required.
And sorry to slow you down, but just in case you can say, what is the nature of the singularity? Is it a time-like singularity or a space-like singularity?
Well, it's you know, it actually depends on which side you come from, right? I mean, yeah.
I mean, is it like inside a black hole, Schwarzschild black hole, where, you know, it's a space-like singularity, or is it like a region? Is it like a world line or something where the curvature blows up? Is it a time-like? Just in case you happen to.
Well, I mean, so if you look at let's talk about it maybe in a moment when I talk about these trajectories.
Yeah.
It's a kind of a natural place to talk about this.
Can I ask a question?
Definitely.
David? Yeah. So for the case with the negative coupling, is there a sensible space-time solution outside of R equal to R1, in which perhaps there's a weak rotation that happens between T and X?
Well, yeah, so let's maybe have this conversation also in like 5-10 minutes.
Okay.
Because I'll say some relevant things for this.
Okay.
Yeah, so let's talk about related things. You know, so here is what I want to do. Again, I'm not. I suspected that I'm going to be very late, so I didn't even put the details here. Again, they're in the paper. You look at the string in the geometry that wraps the S1 and looks like a particle traveling along some trajectory phi of t. You know, the radial position is a function of time. Now, it's a completely standard exercise. You can write down the equation for this particle when it has some energy E, and this is the equation you get. So for positive coupling, remember this F1 is bounded from below by 1. And so you just get some smooth trajectory that describes the particle, let's say, starting in the ADS3 region and moving towards large phi. It takes it, I think, an infinite time to get all the way to the linear dilaton boundary. So everything is good. Like you have these trajectories, you can do semi-classical quantization of them, and they are the ones that give those states of the long strings that I was talking about in the beginning. For negative coupling, this is the F1. Phi is defined, I changed variable from R to phi again. And you see what happens here is that if you look at what happens to such a string as it goes towards the boundary, F1 approaches -1. And so now it's really important whether this quantity with F1 replaced by -1 is positive or not. So if it's positive, in other words, if the energy is smaller than R over LS squared, then you get a smooth trajectory for all T. You know, like phi of T is just some smooth function that you can solve for. If the energy is larger than this, which it turns out essentially it's exactly the same as this energy smaller or larger than epsilon c for the black hole. Again, you can check precisely. Then you encounter a singularity. At some point, this denominator goes to 0, right? Because F1 is -1 and the energy is larger than.
So it was phi the radial location of the long string?
Yeah, phi, like what I called R before, I keep switching from phi to R and back. So I write R as, well, you can see it from here, right? So this is F1, and the same F1 is here written like this. So basically, phi goes to infinity is like, I think R goes to infinity.
So the low energy strings seem to go beyond the singularity, you're saying?
Yeah. Well, yes, I'll actually say that in a second. So low energy strings, well, any strings travel along these trajectories. If the energy is low enough, they just go. And if the energy is larger than the critical value, they encounter the singularity at a finite value of phi. And our interpretation of this is that they do not, these trajectories do not give well-behaved states in the quantum theory if you try to quantize. But the states with energies below this bound are fine. Now, so first of all, this story gives you some interpretation of what does this upper limit mean on the energies. You see it already in the classical problem that the strings actually when you look at it more carefully, if you do a better job than is done here, you see these trajectories kind of reach some value of t and then turn around and go back in time. So that's what I mean by a nice interpretation of the upper limit. But also, as Shiraz just said, we always can go through this singularity at r equals r1 without even breaking a sweat, because that's the place where f1 vanishes, and this thing is always fine there. Yeah, so there's no problem with going through the singularity. And in particular, what we learn most importantly is that if you want to understand the physics of this model, if it makes sense, you have to look at the region beyond the singularity, because this is where this problem occurs that kills the trajectories with energies that are large enough. So this...
And this was an exact CFT analysis, right? CFT of the long strings.
No. This, well, what I described here is just some gravity analysis. I took the background and I asked what is the geodesic equation for a particle moving along a trajectory phi of t and wrapping the circle.
But couldn't you also do a CFT analysis for the deformed long string theory?
Yeah, that could be. Yeah, we have not done that, but it's an interesting idea.
Okay, thank you.
Yes, but you know, the thing I want to stress is that the fact that nothing special happens to this trajectory at the singularity, that you know, if k is large enough, etc., that's not something that you need to do string theory for. The gravity analysis is good enough there. It's only when you get to the vicinity of this singular point that you have to start getting worried. Yeah, so this story also feeds the conclusion from the thermodynamic analysis that the region beyond the kind of zero temperature singularity must be included to understand the thermodynamics. Now, beyond the singularity, the signature of T and X is flipped. And it's actually an interesting story that, again, we haven't really understood well enough. You know, there is this story in quantum field theory where you have some Lorentzian problem, like say, I don't know, particle propagation in an electric field, and you, for some reason, want to analyze it in Euclidean signature. So you weak rotate to Euclidean space, but then various things like an electric field get an I in front of them, right? So you can do some Euclidean problems, but with various I's in the, say, background fields that tell you that what you're really interested in is the Lorentzian problem. There's lots of examples like this, including, by the way, the sigma model on ADS3, which a lot of times people rotate to Euclidean signature. But the point I'm trying to make is that there you kind of do it by hand. You're interested in some Lorentzian problem and you weak rotate to study it in Euclidean space, but you still remember what you need to call time. Here, something similar seems to happen as a function of the radial coordinate. As this particle goes around it, it goes into the region where t looks space-like and x looks time-like. However, it seems to us that you still need to interpret t as time and x as space for all the reasons. Well, it should be clear from what I'm talking about like when in this whole analysis of the whether the trajectories are regular or not, and whether at late times you get to infinity or not. This is what it's all about. Now, this definitely requires more work, which we did not do. So let me not comment on it further. But I think there's some interesting issues here as well. So yeah, so I really should be finishing. So let me just say a couple of a few last things. One, if you look at these backgrounds with the -1 in the harmonic function, if you ever saw this paper by Digraph and company from 2016, you'll see very similar looking formulae there. They call it negative brains, and they have some stories about them. There are lots of similarities between what happens there and here, but from my perspective, the most important difference is that we need to use the signature that is inherited from the region near the strings, whereas from their perspective, you know, say you take flat space, you put D3 brains with a negative n, negative number of brains, and there you use the opposite association of time and space, the one that's natural at infinity. So I don't know beyond that what is the relation and what you know their story means. A lot of the words you'll see in that paper are similar to what happens here. We generalize this whole story, at least as far as the classical trajectories go, to theories with arbitrary combinations of all these other deformations. Bottom line is that you find the exact same story, but you know, in a much more general setting. There's lots of couplings, lots of regions in coupling space, and they all work the same as here. And one thing that I feel like people really should revisit, there was shortly after ADS-CFT, people tried to add the 1 to the harmonic function of the D3 brains in the hope of extending the holographic duality between n equal 4 superring mills and ADS5 crosses 5 to some richer thing. And people like Ken Intriligator suggested that you should think about it as some irrelevant deformation of n equal 4 superring mills. So we repeated our black hole calculations for that case, and everything works well there as well. I really feel like there is some analog of TTbar for that case, and there's a lot of interesting things to be discovered about this. I don't have time to talk about any of the specific results here, but certainly it's you know, something that, like, if you have any good ideas about, I'm certainly going to read your paper with a lot of excitement. Now, there's lots of open problems that I don't have time to list. To me, what this work emphasizes, like everything I said today, both about the singularities and the stuff in the beginning, it basically emphasizes the need to understand ADS3 CFT2 much better, because using these kinds of constructions, it will lead to a better understanding of dualities with other asymptotic boundary structures. You know, we've seen linear dilaton backgrounds, things with Hagedorn density of states, spacetimes with a finite entropy. It also would help, like I say here, to establish whether singularities of the sort we encountered are resolved in string theory, and if so, how. So, you know, I definitely think that there are some good things to do here. Anyway, I spoke enough, so let me stop here and yeah.
Thank you, David. Let me ask everyone to unmute and please thank David for some more questions.
David, thanks a lot for a very beautiful and clear talk. I know we already talked about it, but just one small thing. At the singularity for this negative sign, does the string coupling blow up?
Yes. Mm-hmm.
It does blow up. Okay. So it's not a singularity in the bulk we could, I suppose, hope to understand through alpha prime corrections, at least in this frame.
I would say I agree with that, but you know, this is one of the many reasons why I think it would be great if we could understand it from the boundary point of view.
Yeah.
See, basically, my hope was and still is that one day we will have a detailed understanding of, you know, ADS3 crosses 3 cross T4 is the same as this. And now we do this deformation. In the bulk, it does this. There is a singularity. There are all these other regions. But the boundary theory tells us exactly what to do. So that's kind of the outline of some, you know, long-term project that I may or may not be able to achieve.
Thank you. Thanks a lot.
David, could I ask you about the k=1 story that we've been hearing about over the last year or so? In that situation, everything, the whole context, I mean, there are claims that everything is much simpler. This radial direction sort of disappears, and the boundary theory just becomes the theory of the long strings, if I understand right.
Well, no, not really. So I'm not a big expert on what Rajesh and company are doing, but the whole point is that there are no long strings, right?
Well, no, there are no short strings.
No, there's no continuum, I guess is what I'm trying to say.
Right. There's just one momentum mode of the long strings, just P equals 0.
But, yeah, so there's no continuum. There's a discrete spectrum. So my limited knowledge, my impression is this, that to a first approximation, what Rajesh and his friends are doing is completely orthogonal to everything I talked about. It is orthogonal to everything I talked about in two ways, but in the end, I'm going to say that it doesn't mean that there's not interesting things to do there in this context. So it is orthogonal to what we're doing in two ways. One, you know, they talk about k=1. But the truth is that there are lots of theories with k=1, and most of those theories do not have we know for sure that they do not have the features that they talk about. You know, for example, they do have a continuum. I mean, you know, like say there are ADS3 crosses 3 crosses 3 crosses 1 theories. There are theories that I forget, like ADS3 crosses 1 cross T2. Theories that have k=1, and we can just analyze them using the exact same tools that I used here, and they have a continuum. Now, this is not to say that what they're doing is wrong, it's just different. The second way in which what they're doing is orthogonal to what we're doing, which may or may not be related to the first way, is that, you know, they do ADS3 crosses 3 cross T4 with k=1, and naively you might think that what they're doing is the theory of one 5-brane and P fundamental strings bound to it. But we know that is not true. And the reason we know it's not true is that we can, by U-duality, relate that system to another one which also has a throat. Like, we can discuss this, but this is not the topic of the seminar. So I would say that my impression, partly from talking to one of Rajesh's collaborators, is that in these two ways, what they're doing is kind of orthogonal to what we're doing. Now, however, you know, if it's really true that they have a duality between ADS3 crosses 3 cross T4, and some specific definition of it at k=1 and T4n mod Sn, that's excellent. Now do the deformation of this ADS3 that I'm talking about. So the question is, does their thing have such a deformation or not? Since it is orthogonal to everything that I did here, I don't know the answer to this question. But if it has such a deformation, then it's guaranteed to be the TTbar deformation in the block. I could explain this comment, but it doesn't really matter right now. So in principle, it's possible that their formalism can be extended to study such irrelevant deformations of T4, you know, the block of the symmetric product that they're talking about by TTbar, and provide a bulk description of it. And if that is possible, that would be great. That would be an example where you can.
So actually, my question was just following up on one or two things that you said. I mean, the TTbar deformation that you talked about in the deep UV becomes the theory of the NS5 brains for the good side.
That's right.
I was wondering in the K equals 1 what you expected, if it was possible to do this TTbar deformation on the world sheet. I was wondering what space-time you would expect in the deep UV. Would it be a theory of one NS5 brain? Does that thing make sense? Or would it be something further? Could you hope to get string theory in flat space by doing this?
Okay, so my attitude to this is the one I said, that I'm pretty sure with maybe 80% confidence, and the main reason for the 80% as opposed to 100 is that I never worked on it, is that their duality is not directly related to 5 brains. So I would be surprised. Well, first of all, there is no little string theory of a single 5 brain, as you know. But just in general, I would be surprised if what they get has to do with 5 brains at all, like if they manage to do this deformation. Now, flat space, I believe it cannot be, because it's the wrong Hagedorn, as far as I remember. You can easily show that it's. I mean, the quick way to see that is that you have the Hagedorn of 4 transverse dimensions, not 8. Okay. You know, like the string theory Hagedorn is just the Hagedorn of 8 transverse dimensions, right? Same light cone gauge.
Yes.
And from this thing, you'll get that for 4 transverse directions. So it's going to be the wrong Hagedorn. But I really don't have much to say about any of this. Like, I don't know if they can do this deformation in their thing. If they can, I don't know what they will get. The only thing is that they have to get these energy formulas and beta Hagedorn that I showed you. But I don't think, I would be very surprised if it has to do with 5 brains, because the starting point doesn't have much to do with 5 brains.
Thank you.
Yeah. All right. So
It's already midnight.
yeah.
Let's all thank David again.
Yeah, it was great. It was fun visiting you virtually, guys.
Thank you so much, David. Thank you for taking time late at night.
I had fun. Bye. Good night. Or I guess good morning for you.